Welcome to yet another class. I'm Dr. B, your chemistry teacher, and today I'm going to be discussing with you the Pauli exclusion principle. Remember that we had discussed something concerning the Hund's rule, and this is no much different from the Hund's rule, the Pauli exclusion principle. Now, do not forget that in this class, we expect you to share our videos and subscribe to also this channel, Dr. B Science Classes. And then you also, when you share them, tell your colleagues to subscribe. Okay, and then when they subscribe, they'll have these videos pop up as soon as these videos are uploaded online. Now we have a Facebook page as well, Dr. B Science Classes. In the Facebook, when they go there and type that in, all you need to do is to follow. You like, you share, leave your comments, even in question form, we are going to do what? To attend to them. But importantly, on the Facebook, Dr. B Science Classes, please do hit the subscription button. And in Facebook, Dr. B Science Classes, do not forget to follow. Alright, now we are going to look at the Pauli exclusion principle. Do you know that this principle was being promulgated by a man who is called the Wolfgang? Okay, that's his name, Wolfgang. So he was the person that promulgated this, the Wolfgang Pauli. Okay, and this was in about 1925. Okay, about 1925. That was when Wolfgang Pauli decided in 1925 to start talking about the behavior of electrons in an atom. So his discussion about, his concern about the behavior of electrons in an atom was what gave rise to the Pauli exclusion principle. And it was not enough that he was discussing about the behavior of electrons in an atom, so he went further to discuss about the behavior of fermions. He discusses the behavior of fermions. Okay, and the behavior of fermions, he started discussing this about 1940. Okay, so you could see that between 1925, when he was able to discuss the behavior of electrons, and to 1940, he was also able to discuss the behavior of fermions. Quite little particles, tiny particles, microscopic particles of an atom. And that won him a Nobel Prize in 1945. So in 1945, the Wolfgang Pauli himself, the owner of the Pauli exclusion principle, won a Nobel Prize. And that makes this very whole thing quite interesting. Now, there is a discussion about the Pauli exclusion principle about, in the quantum mechanics and also in the classical mechanics. You can say the statistical thermodynamics aspect of the explanation of Pauli exclusion principle, which is the quantum mechanics and also the classical mechanics. Now, we'll dwell very much on the classical mechanics and not the quantum mechanics. But however, what does the quantum mechanics say about the Pauli exclusion principle? Do you know that in quantum mechanics, we talk much about quantum states? And in quantum states, we talk much also about the microscopic particles, the fermions, alright, the electrons, the photons. Those are the things we discuss in quantum mechanics. You can call it statistical thermodynamics. Now, what quantum mechanics simply say is this: that there are quantum states that build up the theory of the quantum mechanics, but that it is not possible for you to have more than two or more identical particles. That is quite impossible for you to have two or more identical particles with half integer spin simultaneously occupying the quantum states. That's what quantum mechanics says. That is the theory, because the Pauli exclusion theory itself is the heart of today's chemistry, because it discusses more of electrons, about more of the microscopic particles of the electrons, and in that way it discusses much also about the about the electronic configurations of elements defined from their atoms. So the Pauli exclusion principle is the basis, in fact, is the heart of chemistry. Now, what quantum mechanics is saying is that for all quantum states that obey quantum mechanics must also obey the principle, or the Pauli exclusion principle. So there is no way you can have more than two or more identical particles, all right? Now those particles are talking about things like the electrons, okay? There's no way you can have two or more of them, those particles, with the integer, with their various half integer spins occupying the same quantum state. Now, away from that, what does classical mechanics talk about? This very Pauli exclusion principle, because that is what quantum mechanics says. And you can see that from quantum mechanics, there is already an identification or an alliance, as a matter of fact, with the theory of Pauli's in its exclusion principle. Now, what does classical mechanics talk about? Now, I want us to know that the classical mechanics discussion on Pauli exclusion principle is based on the quantum numbers. I hope you know that we have 4 quantum numbers, and that we have the principal quantum number, we have the principal quantum number, which is n. We also have the azimuthal quantum number, or you call the subsidiary quantum number, which is L. You also have the magnetic quantum number, which is M, and then you also have the spin quantum number, which is S. These 4 quantum numbers, the principal quantum number, the azimuthal or subsidiary quantum number, the magnetic quantum number, and the spin quantum number, play serious role in the Pauli exclusion principle described by the classical mechanics, or the classical thermodynamics, or classical point of view. Now, what this classical mechanics simple says is this: is that, look, there is an atom, and in every atom there are shells. Of course, you know that we have the K shell, the L shell, the M shell, and so on. There are shells, and in these shells there are subshells. Okay, and in these subshells, for each of these, you have the S, P, D, F subshells. For each of these shells, you have their subshells. Now, the classical mechanics simply says, it says, look, for each of these subshells that you have, there is no way you are going to have all the four quantum numbers identical in each of these subshells for this particular shell. Yeah, he's saying for every of the orbitals, the s orbital, p orbital, d orbital, f orbital that fall into the various subshells, you cannot have electrons existing in that subshell possessing the same or identical quantum numbers for all of them. Then that is the Pauli exclusion principle. The Pauli exclusion principle is based on 2 things. That one, you cannot have more than 2 electrons in every orbital. S, P, D, F. You can't have more than 2 electrons in every orbital. And 2, that the electrons must exist with opposite spins. The spins must not be the same. And this is classical and more of what we discussed in the Hund's rule. Check my former lecture. Those are the 2 basic principles of the Pauli exclusion. It says that 1, you cannot have more than 2 electrons in a particular orbital, S, P, D, F. And again, that even when you have 2 electrons, the 2 electrons must not have identical spin. Now, it is believed that for every subshell that possesses orbitals, that each of the orbital will definitely have an identical principal quantum number, because that is actually attributed to the subshell. That each orbital will also have an identical azimuthal or subsidiary quantum number, and also have a magnetic quantum number which is identical. But that particular orbital cannot have the same spin quantum number. And that is why the Pauli exclusion principle simply put it clear that for every atomic orbital, there cannot exist more than 2 electrons. And the 2 electrons that exist in that singlet state, those electrons, or in that particular singlet or double state, those electrons must not possess the same spin. Which means it is believed that while in that orbital you have the same principle assumed to a magnetic quantum number, you cannot have the same spin quantum number. And this has gone a long way to unravel so much about the theory of chemistry. Now, do you know that the principal quantum number is 0? Of course, that now for this particular shell, okay, you have a subshell. Now the subshell will have a principal quantum number which is 0 attached to what? To the orbital. The azimuthal quantum number is 0 and 1. Okay, so you have the principal quantum number n, which is 0. You have the azimuthal or subsidiary quantum number, which range from 0 and 1. Okay, and then you also now have the magnetic quantum number, which is either minus m or plus m, depending on the increment of 1 in the process. And then you also have the spin quantum number, which is either minus s or plus s, also depending on the increase of 1 in the process. So if you have the s subshell, for example, the principal quantum number is 0 across all the electrons in that particular subshell. It's identical. The azimuthal or subsidiary quantum number, which is 0 and 1, is the same for all the electrons across that orbital because it's identical. The spin quantum number, the magnetic quantum number, which is negative or positive, is also the same, arising from the subshell that holds that orbital. The electrons will possess the same magnetic quantum number. But when it comes to the spin quantum number, it is not true. It's not the same. It changes. And that is the core of the Pauli exclusion principle. Now, take a look at this diagram that we have here. You will see that this is the 1s orbital, and this is the 2s orbital, and this is the 2p orbital. Of course, the 2p orbital has the px, py, and pz orbital. And then you now have the 3s orbital and the 3p orbital. From the Pauli exclusion principle, it means that from the 1s orbital, which is the very first orbital, they can only have 2 electrons maximum that can occupy that orbital. But these 2 electrons that occupy this orbital will have the same principal quantum number, the same azimuthal quantum number, the same magnetic quantum number, but cannot have the same spin quantum number. And where there are the same spin quantum number, there is a possibility for a collapse of that atom. That's just implications. So you will have if there are 2 electrons, for example, you have helium with the 2 electrons, the 2 electrons will definitely have to fill this first orbital before any other thing. And the filling of the orbital will be such that the spins are in opposite direction. So the spins are always plus half and minus half. No 2 spins will have the same direction. The same direction will definitely have done what? Will have caused a collapse of the atom. Of course, that is one of the reasons why you still have the atom of elements still standing. And after this filling, you move to the 2s orbital to fill the second s orbital. And 2 electrons also with opposite spins will have to do what? Will have to come in. And then from the 2s you go to the 2p orbitals. You can see that there is a first filling of these orbitals in singlets, and then it now comes into the doublets, where you now have to. In the doublet, the Pauli exclusion principle must be obeyed. That is why you have the second electron pointing down, meaning that it's showing downward spin, negative spin of the of the spin quantum number. So the Pauli exclusion principle is very simple. It's not really much about the arrangement of these particular electrons in their orbitals, like in terms of the Hund's rule. But the Pauli exclusion principle is interested in what happened around the spins arrangement in the various orbitals. And according to the principle, all quantum numbers in a particular orbital for the electrons are the same, are identical, except the magnetic quantum number. And in that case, the arrangement of the spin must be such that one is opposite the other. And this particular theory, this particular Pauli exclusion theory, has led to so much relevance. And one of its relevance is in the total explanation of the electronic configuration of elements. To be able to explain, to be able to write, because for example, when you have lithium, you say lithium is 3, and then you say lithium is 1s2, 2s1. Okay? Now, for you to be able to write, to understand, to explain the electronic configuration of elements, you must give thanks to the Pauli exclusion principle that was being coined by Wolfgang Pauli in 1925. Now, another advantage is in the understanding of the nature of chemical bonding. For you to be able to understand the nature of chemical bonding in elements, you must give thanks to Wolfgang Pauli in the Pauli exclusion principle. If you don't understand the Pauli exclusion principle, you find it difficult to also explain chemical bonding in compounds. Now, another advantage is in the modern electronic, the modern theory of an atom. All right, to understand the modern theory of an atom, okay, you must also be able to be abreast with the Pauli exclusion principle. And how about in quantum mechanics? It plays a role there, like I started saying. Even in physics, the Pauli exclusion principle plays a serious role in astrophysics. So you can see that it is not only in chemistry that the Pauli exclusion principle plays significant role, it plays role also in astrophysics. Especially in astrophysics, you can see it playing its role there. So this can go on and on, talking about the advantages or relevance of the Pauli exclusion principle. But let me not bore us with so much of them, for you can just read from there. But I want you to understand two basic things out of the Pauli exclusion principle. Not all the quantum numbers in a particular orbital for electrons that occupy it are identical. Basically, the principal azimuthal magnetic are identical, but the spin quantum number varies. 1. 2. That for every orbital there must not be more than 2. There must not be more than 2 electrons occupying such an orbital. And even if the 2 are occupying, which is 3, that the 2 must not have the same spin arrangement. I'm sure that you have enjoyed this class today on the Pauli exclusion principle, and next time we'll bring something very new again to explain our throw light, for us. Please do not forget to subscribe to this channel. Please don't forget to also share, and when you share, encourage them to subscribe to be part of what we are doing, beautiful thing we are doing here.